All right, welcome to The Explainer. Today we're diving into something that's completely invisible but is powerful enough to, well, hold our entire world together. We are talking about electric charge.
You know that feeling, right? You reach for a car door handle and zap. Or you just watch in awe as lightning tears across the sky. That's not some random fluke. That's a direct, personal experience with electric charge. And that's exactly where our story begins today.
So, how in the world do we go from a mysterious little spark to understanding a fundamental force of nature? Well, the story starts with a few really simple but incredibly telling experiments. So check this out. Early scientists noticed a really fascinating pattern. If you took two glass rods and rubbed them with silk, they'd actually push each other away. Same thing happened with two plastic rods rubbed with fur. They also repelled. But, and this is the kicker, when you brought the charged glass rod near the charged plastic one, they pulled toward each other. They attracted. This was the first giant clue that there wasn't just one type of electricity. Something more was going on.
And those super simple experiments led to a really powerful idea. There must be two different kinds of electric charge. It was actually Benjamin Franklin who gave them the names we still use, positive and negative. By convention, the charge on that glass rod was called positive, and the charge on the plastic rod was called negative. And just like that, you have the first fundamental rule of electricity. Like charges repel, and unlike charges attract.
This essential difference, this plus or minus quality, is called polarity. It is the why behind all that pushing and pulling we just saw. That simple positive or negative property is what dictates how every single charged particle in the entire universe is going to interact. It's a pretty big deal.
Okay, so we've identified two types of charge. Now let's see how this discovery leads to a few fundamental rules of the game for electricity. These are the basic properties that every charge in the universe has to follow, no exceptions.
There are three really key properties. First, additivity. This one is super straightforward. Charges just add up, like normal numbers. If you have a charge of +5 and you add a charge of -2, your total is +3. It's that simple. Second, conservation. Now this one is huge. You can't create charge out of nothing and you can't destroy it. When you rub a rod and a cloth together, you're not making charge, you're just moving it from one object to the other. The total charge of the whole system stays exactly the same. And third, quantization. This one can bend your brain a little. Charge isn't some smooth, continuous fluid. It comes in tiny, indivisible packets. The smallest possible unit of charge is E, the charge of a single electron. Every charge in the universe is a whole number multiple of that tiny fundamental amount.
But hang on, if charge comes in these tiny little steps, why does it seem so smooth to us? Why don't we feel the individual packets? Well, the reason is that this basic unit of charge, E, is just unbelievably tiny. When we're dealing with charges in our everyday world, we're talking about trillions upon trillions of these basic units. The individual steps are just far too small for us to ever notice.
This is a fantastic way to think about it. Imagine a dotted line. From far away, it looks like one solid, continuous line, right? Your brain just smooths it over. But if you get right up close to it, you can clearly see the individual dots that make it up. Charge is exactly the same. On our human scale, it looks continuous. But if you could zoom all the way down to the microscopic level, you'd see that it's actually made of these discrete little dots of charge. So, we know what charge is and its basic rules. But how can we actually calculate the force that it creates? How do we quantify that push or that pull? Well, this is where the work of French physicist Charles Coulomb comes in, and it is an absolute game changer.
This is it, Coulomb's law, the bedrock of electrostatics. It's a powerful equation that lets us calculate the exact force between two charges. What it tells us is that the force, F, is proportional to the size of the charges, Q1 and Q2. But crucially, it's inversely proportional to the square of the distance between them. That inverse square part is key. It means if you double the distance, the force doesn't just get cut in half, it drops all the way down to 1/4 of what it was.
To really get a feel for the kind of power we're talking about, let's make a quick comparison. We all know gravity. It's what holds us on the ground. It feels pretty strong, but how does the electric force stack up? Well, The electric force between two protons is 10 to the power of 36 times stronger than the gravitational force between them. That's a 1 with 36 zeros after it. It's a number so astronomically large it's almost impossible to comprehend.
This quote really says it all. Sure, gravity might run the show on the scale of planets and galaxies, but down at the level of atoms and molecules, the level where our world is actually built, the electrical force is the undisputed king. It's not just a little stronger, it is enormously stronger. It's not even a contest.
Okay, but how does one charge know that another one is over there so it can push or pull on it? The old idea was something called action at a distance, which always sounded a little bit like magic. The modern idea is much more elegant. Charges create an invisible influence in the space all around them, and that influence is what we call the electric field. So instead of thinking about one charge acting on another across empty space, think of it this way. A charge actually changes the space around it. It creates this field. Then, when you put a second charge into that field, it's the field at that exact spot that exerts the force. It's a subtle shift, but it's a profound one. We go from two objects interacting to one object interacting with the field right where it is.
So what happens when you have a whole bunch of charges all interacting at once? You might think the math would get insane. But luckily, there's a beautifully simple rule for this, called the principle of superposition. It just says that the total force on any one charge is simply the sum of all the individual forces from all the other charges. You calculate each force one by one, and then you just add them all up as vectors, which just means you have to account for their direction. This elegant idea is what lets us figure out what's happening in even the most complex systems. We've gone all the way from static shocks to invisible fields, but let's bring this all back home. Why is understanding this force so incredibly important? Because, as it turns out, this force is responsible for, well, pretty much everything. The reach of this force is just staggering. A mass of 40% of its job is just shaping the very structure of atoms. Another 30% that governs all of chemistry and biology, how molecules stick together, how life works. 20% is basically all of our modern technology. And that last 10%, that's everyday stuff like why glue is sticky and the force of friction. It is truly, truly everywhere.
So when you boil it all down, it's this. The same force that zaps you when you touch a doorknob is the force that holds the atoms in your body together. It drives every chemical reaction, it makes tape sticky, it powers your phone. The solid world that we all experience is really just a large-scale, visible consequence of these simple, fundamental, invisible rules of electric charge.
We started with a simple shock, and we ended with the force that architects our entire world. It's a powerful reminder that sometimes the most profound principles of the universe are hidden just beneath the surface of our everyday lives. It really makes you wonder, what else is out there, hiding in plain sight, just waiting to be explained?